In recent years, the close relationship between threats to the architectural heritage and environmental changes has been pointed out. Namely, hydrologic processes are able to accelerate the decay of historical buildings and sites. It becomes clear that the management of the waters and that of the built heritage are strictly interdependent. The accurate knowledge of the subsoil, especially in highly anthropized areas, is claiming an increasing attention to understand the damages of the built heritage and to properly define conservation strategies. Accordingly, in recent years, architectural and archaeological conservation studies have undergone an interdisciplinary and multi-scale approach to this matter. During the last decades, Egypt experienced a strong increasing of stone monuments damage due to the groundwater rising, strictly related with the abrupt growth of population and a huge urban drift. These phenomena fully pose the country in the problem of very critical conservation tasks. The problem is widespread, especially in Cairo, where the conservation of historical buildings is a matter even more complex, which is influenced by several key factors such as the cultural context, the urban and anthropic activities, the intrinsic features of a vast and heterogeneous architectural heritage, and the environmental conditions. Here, we report the preliminary results of a multidisciplinary investigation carried out on the medieval monuments of Cairo by an Italian-Egyptian team. The aims are the study of the state of conservation of building materials and the dynamics of their deterioration, the study of the relation between material decay and anthropic activities, climatic factors, and pollution levels, and the last goal is to identify and systematize the vulnerability levels of the monuments to delineate adequate programs of control, management, and intervention. One of the main topics developed is the study of the deterioration mechanisms of stone materials in medieval walls, connected to the capillary damp rising from the ground. The research examines some historic buildings in different areas of Old Cairo. The intersection of data collected on field with those relating to underground water and environmental factors has allowed us to focus on some aspects of the problem. The study proceeds via the survey of representative case studies in relation to water rising and sets up criteria for the technological knowledge of the buildings in a conservation perspective. The proposed procedure couples in a multi-scale approach several information, from the urban to the building scale, then the masonry, the decorative elements, and the individual stone blocks. Indeed, a set of desk-based and on-field investigations has been applied to significant buildings, selected for their historical and architectural relevance and for the enhanced level of the grade. The investigation has proceeded through architectural survey, identification of building materials and their alteration processes. Then a selection of samples collected from materials under the touch from limestone blocks was made available for laboratory characterization. These latter were carried out to establish on a more quantitative level the decay processes attributable to soluble salts, polluted water, and air. Several scientific evidences of environmental concerns in the underground waters of the Nile Basin were recently provided. Namely, numerous studies report of a widespread seasonal rising of the water table, the lowering of the river level, the salinization of soils in many places of the valley and delta. Climatic changes and environmental consequences of anthropization are identified as major players of these degenerative processes. The realization of the Aswan Dam in 1968 induced several changes in the hydrogeologic asset of the valley. The drainage of the groundwater exerted by the Nile has been altered, as well as the progressive salinization of soils, nitrates and phosphates, for example, due to the major need of fertilizers, is registered southward along the river, where, moreover, the traditional irrigation carried out by flooding the fields contributes to the hyperhydration of soils. If combined to the rise in population, new fields at the boundary with the desertic regions are progressively involved in this process. The same increasing of salinity has been also detected in the Nile Delta aquifer in combination with different sources, marine water intrusion and deep groundwaters. In Delta region, the anthropic effects also contribute with the water consumption by industrial activities and the waste management in the urban areas. The effects on the architectural heritage linked to rising of the water table and to pollution of the groundwaters have been described in Egypt for decades. From Abu Mina to Thebes, no Egyptian site can be considered free from the threat of the groundwater rising due to the cultivation of arid areas. By the evaporation from the surfaces of soils and buildings, shallow waters can rise up through the alluvial levels with their content in salts. The cyclic stages of dissolution and crystallization of salts lead to the progressive rock disintegration, and the traces of the rising water are evident in almost all stone monuments along the valley. In Cairo, this process is widespread, with the astonishing decay of the architectural heritage, as claimed since the UNESCO report of 1980. Today the problem is still unsolved, and cycles of on the groundwater raising and evaporation are destroying the lower parts of many historical buildings. It should be considered that in Cairo the annual rainfall sums to less than 40 millimeters. Humidity occurs in the range of 45 and 84%, and daily evaporation ranges between 2.5 and 15 millimeters. The geological setting of the Old Town consists of an intercalation of alluvial sediments and relics of former settlements in layer up to 15 meters thick. Below, clay formation for a thickness of up to 4 meters and sands up to 100 meters in depth occur. Each formation hosts a proper water layer, supplied by different processes. The clays catch waters from rain, irrigation, and leaks from pipelines and reservoirs waste fluids. The rise of population in Cairo from 14 to 20 millions in the last 17 years has highly influenced the changes in the depth and contamination of the water table. The poor knowledge of the subsoil and the scarce control of the pipelines contribute to increase the criticality level of the system. The worst situation appears in the Quaternary water layer of the northeast of Cairo, where contamination down to 40 meters depth has been described. This layer tends to feed areas characterized by an intensive water pumping. A wide range of total dissolved solids, as well as intense contamination levels by nitrates, sulfates, have been described in relation to anthropic activities or wastewater management. Recent studies claimed a role by abandoned reservoirs or pipelines as concentration steps in the groundwater circulation, with adverse effects on the adjacent buildings. The variety of materials of the wide architectural heritage in Cairo has led to limiting the first phases of this study to the masonry materials, with special attention to the limestone blocks. Excluding the stone blocks reused from southern archaeological areas, almost all limestone used in the historic buildings of Cairo since pre-dynastic times comes from the Mokattam formation, which mainly outcrops on Gebel Mokattam and from Giza Plateau to the hills in East Cairo. The most valuable material, compact and hard, came from the ancient quarries of Tura Mazar, and a less compact limestone from shallow marine waters was carried from the outcrops of the Giza Plateau. A successive formation, the Ma'adi unit, gives a marly porous limestone. Nowadays, active carriers are located at L1, which also provide materials for restoration works in the region. The overall set of building materials associated to the definition of Mokattam stone emerges from this brief survey, characterized by a relevant variability in composition and texture. The different textural characteristics of the Mokattam limestone from the various carried outcrops are thus linked to different decay processes and levels. Numerous studies carried out on stones were aimed to assess the main alteration processes. And these processes include dissolution due to the karst processes and acid processes, where atmospheric moisture, acidified with sulfur and nitrogen oxide, react with calcium carbonate and forming calcium sulfate. The same oxides are responsible of the formation of gypsum crusts on the stone surface, combined with dry deposition. The stronger thermal variation leads an internal stress, mainly along the grain boundaries. As a consequence, the stone undergoes granular disintegration with increasing of porosity. The presence of moisture on and in the stones and the salt crystallization inside the pore network may represent a significant environmental factor contributing to stone decay. Initially, we identified the area for the on-field survey in the boundaries of the medieval town. The survey, planned on the basis of the previously available information, was aimed to assess a general level of decay of the buildings and the peculiar damage caused by water rising. The investigation focused on three main districts of the old town: El Gamaleya, El Darb El Ahmar, and Al Karafa, the historical cemetery town at the foot of the Mokattam Hills. We selected 20 historical buildings as case studies scattered in the eastern districts of the Old Cairo: mosques, khankas, palaces, houses, walls, and a portion of the medieval aqueduct. For all the surveyed buildings, a field form was compiled, with observations on the architectural and technological aspects. The urban contextualization, the building materials, and the conservation tasks. A digital survey of selected parts of the buildings was carried out to understand their morphology and to create a support for further mappings. The architectural survey allowed us to document both the technological details of the masonry. Digital mapping of selected walls were then operated with special attention to the qualitative determination of the erosive processes involving the limestones as a function of the appreciable water risings. From the comparison with the available photographic documentation of the same sites, in the last decades, a rough estimate of the incremental step in decay was assessed. Other damage processes of stone were also mapped for the structures involved in the water rising as pavings, to give a more complete frame of the current state of conservation. All the investigated monuments present relevant levels of decay of the limestone in their lower parts. This is the case, for example, of the medieval aqueduct, the Al-Hakim Mosque, and the northern walls. The same critical conditions can be found in some of the most important monuments of the medieval city, such as the Great Mosque of Sultan Hassan and the main Barkuk Mosque. Several forms of decay were detected for the Mokattam limestone blocks, due to a number of chemical and physical phenomena, such as deposits, crusts, honeycomb, and abrasive weathering. Generally, limestone appears largely affected by erosive phenomena, mainly correlated to crystallization of soluble salts. Widespread sulfation phenomena of carbonate surfaces are observed and black cross can be evidenced. In general, these dark black sulfated surfaces are located immediately above the level of the main detached area and thus are somehow connected to the water rising too. The continuous erosion and detachment of the altered stone led fresh surfaces to be exposed and the process to be renewed. Accordingly, the overall degradation of the walls proceeds at a very high speed, and it seems confirmed by the constant presence of white microcrystalline particulate at the ground of the degraded walls. If a general accordance between stone porosity and degradation level can be inferred, in certain cases also less porous stones present conspicuous phenomena. It is thus suggested that the evaporation can drive the process of soluble salt rising and crystallization before their exit to the stone surface. And this process could be the cause of internal stress that solicits the blocks and results in the detachment of the surface layers. To this general trend, effects ascribable to the general air pollution are also visible. Our on-field survey of the medieval town remarks that the height of rising fronts increases while moving toward northeast and lowers in the southern districts. It appears quite clear by mapping the average height of the traces of rising water on the buildings in relation with the ground elevation of each location of the monuments. Exemplar cases are the mosques of the main street in El Gamaleya, where the rising fronts are more than 6 meters high. Here you can see the Inal Ali Yusufi Mosque and the eastern wall of the Al Saif al-Din Barkuk Mosque in Al Muid Street. The evident damaged surfaces mainly concern calcareous stones, with specificities arising from water fluxes, composition and evaporation characteristics. The same conditions can be detected for the wall Calawun complex, the outer wall of the mausoleum on the left and the northern side of the main minaret on the right. Different fascias can be related to stratifications of past and actual phenomena, alternated for years on the considered walls. Disintegration due to the action of dissolved salts in rising water levels is absolutely alarming, and it results in the retraction of the actual surfaces with respect to the original outline of the walls. Rock samples were analyzed, collected from Al-Maridani Mosque, Al-Aqsunkur Mosque, Kalaun Complex, and from the Kanka of Farag ibn Barkuk. The mineralogical and petrographic analyses were carried out using X-ray diffraction and a polarizing microscope. The composition of the studied rocks consists of prevailing calcite with small amount of quartz. Various other mineral phases are observed, such as halite, nitratite, and calcium sulfate minerals. The porosity is low, with pores displaying irregular shape. Remains of microfossils are very abundant, and concerning the rock composition, the present results are in good agreement with the previous studies of the different formation belonging to the so-called Mokattam stone. In particular, we confirm the frequent association in very few amounts of halite and gypsum attributed to a paleoevaporitic process. The same mineralogic phases can be also referred to alteration products of the Mokattam stone surface. That's why, accordingly, we safely attribute the identified phases of the alteration products in a complete agreement with the visual inspection of the sampled wall surfaces. Concerning the degradation of the stone, the most relevant question to be addressed is the active mechanism of alteration, namely, if the chemical species necessary to allow the accumulation of both chlorides and sulfates in the alteration products are provided by the water uprising or by an atmospheric pollution. It is generally accepted that the urban atmosphere in Cairo can be rich enough of sulfate species and also of sodium chloride, by both transported from the near desert regions and from the seas. The main weathering process is strongly related from the rising of the water table, which provides not only the wet environment able to catalyze the rock alteration and detachment, but also the majority of the salts necessary to the development of alteration processes. The studies of the last decades have revealed how the weathering of the stone walls in almost all the historical monuments follow an almost reproducible pattern, where at least 4 zones are discriminated. From bottom to top, the zone number 1 is heavy weathered with stone detachment. The zone number 2 is weathered with mainly halite as alteration product. The zone number 3 is weathered with mainly gypsum and sulfates as alteration product. And the zone number 4 is the unweathered zone with the original surface. On the one hand, our results are in line and confirm these observations. On the other hand, the stratified alteration of the stone walls suggests that the clue of the weathering processes has to be identified in the rising up of the water table. This weathering process, besides providing a loss of aesthetical effects due to the surface alteration of the blocks, appears a more fundamental threat to the stability of the wall stone structure. The stone, in fact, is exposed to weathering simultaneously at the surface and in its interior, with a progressive loss of physical coherence and mechanical properties. Accordingly, we envisage the most serious risk to the conservation of the medieval buildings in Cairo in the rising up of the water table. The main results of this first on-field survey mark an alarming situation for many monuments, in line with previous results in the literature. The present study points out the correlation between the presence of water rising and pollution. It allowed us to define the boundaries of a systematic program of investigation aimed at clarify the different levels of degradation attributable to rising waters, and to organize a hierarchy of opportune intervention activities in Cairo Old Town. The next steps of this research have been clearly focused and planned. A detailed study aimed to a deep knowledge of the physical, chemical, mineralogical, and petrographical properties of the Mokattam stones is mandatory to exploit efficient conservation activities. The comparison between present and past data will be highly desirable to evidence systematic temporal trends, and is hold true for satellite and aerial views and for the cartography. The monitoring of the rising of water through the monuments could be performed by the cyclic survey of the surface weathering levels. Moreover, durability and its parameterization appears a very useful step to be developed, including combined effects of different factors and porosity types. Finally, a detailed review of the geological settings of the region, including the specificity of the alluvial and surficial levels in relation to the anthropic colonization and use of the soil, will be also necessary. Thank you very much for your attention.